Welcome to data. We're going to be looking at what you do with the data you collect and how to display it correctly. Now, this may start to seem like the more finicky part of class, where I'm going to give you a bunch of rules that you need to follow, and they just seem like, oh, the teacher's giving us rules just to make us work and take up our time. However, when you're displaying your data, this is about communication. It's about science communication. One of the biggest parts of science is communicating your results, your findings to other scientists so that you can collaborate together so that other scientists can ask even more questions. So it's super important that you're able to communicate what you're doing in a way that's understandable to anyone who takes a look at it. Also, by putting your data into a visual format, you're making sure, or you're starting the first steps into analysis. You're able to see it visually. You can start to see trends, correlations, things like that are going to help you in that first analysis step. So in order to make our data very nice, we are going to follow a couple of acronyms. So we're going to start with data tables first. These are tables you have definitely seen, definitely worked with in math and science classes before, but I want to make sure that you can make the best data tables possible so that you can communicate effectively. And so in order to do that, you're going to use the acronym CRUST. You're going to make crusty data tables. So let's kind of go down what that means. We're going to start with C. C is for columns. Remember, columns are the vertical part of the data. Everything in a column is going to be the same type of data. Similarly, we have R for rows. Rows are the horizontal part of your data table. Now, what goes into a column, what goes into a row can sometimes be down to kind of personal preference. You just have to make sure that you are keeping the same sort of data in columns and the same sort of data in rows. Next, we have U for units. So you've probably labeled your columns and your rows to tell me what kind of data you have in each of those. But you need to go a little bit further and tell me what you're talking about. Are we talking years or are we talking centimeters? Knowing what you've recorded, how you've recorded it, is going to definitely help in understanding your data table. We have S for straight lines, and this applies to the overall readability. Once again, this might sound like a fussy teacher rule to have you do more busy work, but this really is about making your data tables readable and treating them as the super, super important fonts of information that you are. As a scientist, basically all the really hard work that you're doing, especially out in the field, you are collecting observations, data, evidence. All of this is going into a data table. You are then going to base your analysis, your conclusion, everything important on the data that you collected. So you want to treat this data as super important, put it in kind of the nicest little home that you can. So that means making straight lines, making sure it's readable. In your case, just making sure that I can read it, making sure that you can read it as well. Finally, we've got a title. And this is another communication component. Like I said before, you want somebody to be able to just look at your data table and pretty much know what you're talking about right off the bat. What you measured, what data you collected. Now, this is going to kind of tie together your rows and columns, because like I said, every once in a while people change them depending on their preferences. The title is going to make sure that the reader knows exactly which is the dependent variable, which is the independent variable. What is being compared? And I'll show you in a bit kind of a good rule of thumb for how we can make those titles very easily. So let's look at a kind of visual example so we can see each of these crusty steps. So C for columns. Columns are vertical, up and down. Notice in this example, the columns are separating the data by years. Same thing with the R. R is horizontal, and in this case, we are separating by person. So notice that in between the columns and the rows, everything's staying consistent. Years are only in columns, people are only in rows. There's no mixing up in between those two categories. We've got U for units. Depending on what kind of data table you have, every once in a while you can write kind of units at the top and not in every single square, but in this case, we're using it. We know that we're talking about centimeters. And also notice that we have units for kind of both our variables here. We have the units that we measured, and we have the units that we were observing, in this case, years. Now S is for straight lines, always easiest to make on a computer, but once again, just to make everything as readable as possible. And finally, the title. So this kind of takes us back to our hypothesis and how we make a hypothesis. So if independent variable, if I change something, then I will measure something, or I will see a difference in the measure. So if IV, then DV. Title works in the same kind of way. So a lot of times you can write it as the effect of my independent variable on my dependent variable, or in this case, it was more of the dependent variable being affected by the independent variable. So in this case, our independent variable is time, and our dependent variable is growth. So they did human growth being affected by time. And what's really nice is this is also going to apply to our next set of rules. So you start with your crusty data table. Yes, I know there's no Y technically in there, but it's just more fun to say a crusty data table as opposed to a crust data table. But now that we have this, we are going to be building a graph, and we're going to use the acronym WildTubs. Now, for most of us, just looking at a data table, you can get some information from there, but creating graphs, we're making a visual of these numbers, and that's a lot easier for us to begin to interpret, see correlations and trends, which are going to show you how you can use analysis to figure out what's going on in your data, how it's answering your hypothesis, how it's supporting your hypothesis. And once again, there's going to be more finicky rules, like this first one, W, use the whole graph. Basically, that means I give you a piece of graph paper. For your graph, you're using that whole dang graph paper. And it just comes back to readability. It's also going to make it a lot easier on yourself when you need to fit everything on the graph. So just something to remember. I is for independent variable. Our independent variable is going on the x-axis. So remember, the independent variable is something that we're changing, something that we're observing. A lot of times, our independent variable is going to be time. So it's growth, decay, reactions over time. Other times, in a more simplistic experimental design, especially when we're comparing categories, the categories will go on the x-axis, and that's actually going to relate to this next part of the graph, or this next part of WildTubs, where we're talking about line or bar graphs. So whether you're using a line or a bar graph depends on the type of data that's going on your x-axis. So continuous data, like time, that's going to get a line graph. So growth over time is a great example. However, if we are looking at categories, we're comparing two different things or three different things, we are going to use a bar graph. Now, just kind of a hint here, most of the graphs we're going to be looking at and creating are going to be line graphs. They just tend to turn up more when we were comparing quantitative and qualitative data. Remember that quantitative data is going to be more objective, it's going to be more reliable, and so it's that quantitative, that number data, that we usually want to lean on. So especially if your X, your independent variable, can be broken down into quantitative steps, that means that it's going to be a continuous or a line graph. If we're using categories, that's going to be a bar graph. So our D is dependent variable, and that's going to go on the x-axis. The dependent variable is going on the y-axis. Sorry about that. This is what we're measuring, and this is what is dependent on the independent variable. Look back at your previous notes, know that it's a little bit more complex than that, but for now, yes, we can go back to this old factor. The dependent is being changed by the independent, and so therefore that dependent is going on our y-axis. So notice we've gotten through wild, we have tubs to go, but the ILD are probably the most important parts of your graph. Figuring out what's your independent, what's your dependent variable, putting them in the correct places, and then figuring out what's the correct way to display them. This is what I've tried to give you the most practice with some of our experimental design worksheets, but this is definitely something you want to make sure that you have a good grasp on before kind of moving on to the next parts of your graph. So let's get into our tubs section. So T is your title. You have to describe what's happening in your graph. Thankfully, this works just like our titles for the data tables worked. You can use that same formula, the effect of your independent variable on your dependent variable, or dependent variable versus independent variable. What you don't want to do is something like this where you're just saying plant graph. It's a graph about plants. No, we want to be actually descriptive and put in what we're actually measuring. Because if you think about it, plant graph could be absolutely anything, but we are looking specifically at the effect of light exposure on plant growth. So our next step, just like with data tables, is units. And I'll show you later on our more visual example. This is something that you're putting into the labels of the axes. You have to make sure that basically numbers only mean numbers unless they have labels attached to them. So I need to know, are you talking centimeters? Are you talking years? What's going on? Finally, we've got big. This is sort of the same thing as W, using the whole graph, making sure that things are visible and neat. You've done all the work to get the data. Make sure that you are giving it the importance it deserves. You worked on it, so you want to make sure that you are displaying it in the best way possible. Finally, spacing. So numbers need to increase at equal intervals. This is something that is going to happen automatically when you're using a computer, but when you're hand drawing your graphs, this is something to keep in mind. And when we go through our visual examples, I hope I can give you a little bit of a better idea of what I mean by spacing. But let's kind of look at a wild tubs graph example. So looking at this right away, we can kind of see what it's about, see what's going on. In this case, it's parental IQ versus child's age. I might change the title somewhat to say this is the child's perception of parental IQ versus the child's age. As we can see, when the child's age is very young, 4 to 10 years, the parental IQ is very high. When you're little, you think your parents are pretty smart, know everything. However, we see a big drop-off when the child's age reaches those teenage years. That's because once you become a teenager, you realize your parents don't know everything, and in fact, pretty much seems like they know absolutely nothing at all. This kind of continues till the child gets to be in their 20s, and then they start realizing, yeah, okay, mom and dad might actually know something. This is when you start to, move out on your own, maybe even start a family on your own, and you realize, oh my gosh, all those things my parents told me were actually true. So it's kind of a silly graph, but we're going to go through why it works really well for our wild tubs example. So W, it's taking up the whole page. Like I said, this mostly has to do with hand drawing, but for example, if you were to give me, a page and that was your graph there, that wouldn't be great. Don't try and smash things into a corner. Just use extra paper. I'd rather have extra paper than have your graph smashed into some little place where I can barely read it or see what's going on. I for independent variable. So remember, our independent variable here is going to be child's age. The thing that we're measuring that is changing is parental IQ, and it's changing because of the child's age. So that's going to make the age our independent variable, which was y. It's going on the x-axis. And notice that I've highlighted that age. Once again, if there were just numbers, I wouldn't know what you were talking about. Now we jump into, this is a line graph. Obviously, since we have the graph in front of us, it's easy to tell. But if we were looking at the data table, we would see that our independent variable is continuous. It's years. We are looking at something changing over time. Now, if our graph, or if our data was looking at parental IQ versus a child's gender, then we would break it down into a bar for girls, a bar for boys, a bar for others, and all three of those bars would have a separate kind of score. But in this case, we're looking at how it changes over time, and so that's why we have a line graph here. D for dependent variable, this is what is changing. In this case, it is parental IQ. Once again, we have not only put the numbers there, but I've labeled what numbers we're actually talking about. The title, so like I said before, easy as you can either do dependent variable versus independent variable, or the effect of independent variable and dependent variable. All easy ways to do it. Also, you can totally name or title your data table the same thing that you title your graph, because they're showing the same information. Now, U is for units. Notice I've circled years on the x-axis there. That's because if you just say age, okay, what are we talking about? Are we talking about 4 years old? Are we talking about 4 months old? Are we talking about 4 seconds old? You need to put years. This is the standard way of showing units, is you have the label and then in parentheses you'll have the actual units you're talking about. On the y-axis, you are going to see one of the very, very few exceptions to this rule. Since IQ is a made-up concept and it's just understood that, IQ goes from 0 to 200 and they are scores, then you don't necessarily need to put your units there. But that's a super, super, super rare incident. Usually there's going to be something in parentheses that's showing you what that y-axis is actually representing. And then, like I said, W and B, pretty much the same thing, making it big, readable, and when you're using a computer to make your graphs, spacing is going to be pretty easy. But I want to just show you some examples of where spacing might get a little different. check out the top example. I have some tick marks down, and they are not spaced very neatly. So if I start labeling these, 1, 2, 3, 4, 5, 6, this is not going to reflect my data accurately. If I'm talking incremental numbers, I need the same amount of space to illustrate that when you're talking a number line, when we're talking values, there's the same amount of space between 1 and 2 as there is from 2 to 3, as there is from 3 to 4, 4 to 5, 5 to 6. I need to have that illustrated on my graph accurately. In the bottom example, I have my tick marks all evenly distributed, but in this case, I'm not spacing my numbers correctly. I'm going from 10 to 20 to 100 to 110 to 200. This is also going to change the shape of your graph and make any trends that you see very misleading because they won't be correct. This is definitely something that as we start to work with data, maybe try spacing some of your axes incorrectly. See what happens. Even look up sort of the difference between, say, a linear graph and an exponential graph. If you've already gotten into those concepts in math, you'll know that whether or not you make the axes linear or exponential is going to change what the graph looks like as a whole. In this class, we're mainly going to be focusing on linear data. So make sure that you aren't jumping ahead or putting too much space where it doesn't need to be. So let's kind of look through some of this. See if you can figure out what's missing from these various graphs. I'll give you a couple minutes or seconds. So I'm looking at this, and right away, it's not really at the top, but there's no title. That's not a good color. I mean, I could guess this from context clues, but you shouldn't rely on context clues. I don't know what this x-axis is all about. It's got no label and it's got no units. So in between this title being missing, our x-axis labels missing, this is no good at all. Something we didn't really talk about is that this particular graph has two different lines. So we've got the blue line and we've got this red line here. What needs to happen in this case is you would need a key, maybe up here, and you're going to have, a red line and a blue line, and you're going to label, okay, the red line is this, the blue line is that. Put it all in a nice box and make everything more clear. Let's try the next one. So I'd say this is another one. We are missing a title. Even this label on the y-axis is pretty esoteric, I would say. Number of complete games. What kind of games are we talking about? At least with year, this makes sense. Year can be a label and unit in itself if we're talking about actual years, but we kind of have no idea what's going on overall in this graph. So this is another one. Okay, I could figure this out with context clues, but I should not be asking my readers to use those in order to figure out what my graph is saying. Right, like most of these We've got no title up here. Got nice, y-axis, x-axis. Notice we have some spacing issues that start to become very noticeable right here. Basically, we have the same space between 400 and 700, or 17, as we do between 35,000 and 45,000. Also notice we're going from 35,000 to 45,000 to, what's that, 20,000 to 15,000 to 5,000. We're kind of going up and down here. So that is making this graph look way stranger than it needs to be. So we have spacing. Also up here, it would be nice if we could have some sort of key. Let's see if I can even write this. That's going to tell us, what we're talking about. I'm assuming it's years, but I'm not entirely sure. So that's a fun one. Next, kind of take a look. So always first thing, there's not a title. We have lots of variables going on. So we've got divorce rate and per capita consumption of margarine. And it seems to be over, I don't know, I guess these probably mean years. So the correlation that we're saying is that as the divorce rate decline in Maine correlates with the decreasing consumption of margarine, which is an interesting thing to make. Maybe if we wanted to actually correlate those, we decide which one of these is our independent, which one of these is our dependent, put them maybe on the x-axis. This one's kind of all over the place. And finally, just because we haven't seen any, this would be a good bar graph. Using all the wild tubs, as you can see, we don't really need units because we're using categories. In this case, we're defining our categories as things that are useful. And then we're measuring the usefulness in sort of categories that we've made up. So hinders progress, can do without, mildly useful, really useful, must have, do not forget it. But this is all the information that you would need from that. So I hope that helped you guys out, and I will speak to you in our next notes.